people from civil. So you can use the picture that's posted. I didn't get the folder in course assignments. I can't figure out how to move things around on Blackboard 9. You know, we go from Blackboard 8 to Blackboard 9. It's like going from Latin to Chinese. You know, there's nothing that crosses over that I can figure out. So it's in course documents folder. There's a photograph of the core box, and then there's a photograph of the shale bed in there. Of course, shale bed's your big focus whenever you're coring rock, because the shale is the toothpaste. So that's where all the strain action is going to occur. That's where the slippage is going to occur. That's where all the bad things generally occurs. It's kind of like going to a bar that's open after midnight. So anyway, today when we do rock cores, we typically put a photo strip, a digital photo strip along. We actually take pictures of them and have the photo strip along. So I need to upgrade the exercise so it's a little more modern. The rock core sample that I gave you that I did back when I was a PhD student was 31 years old, so it's kind of dated. So I just haven't gotten around to replacing that yet. This week we're going to move on to Chapter 6. And Chapter 6 is dealing with slope stability and landslides. And I have a lot to say about this particular subject because it's near and dear to my heart and my experience. It's called mass wasting, which is the geologic term for mass movements on slopes. All the slopes we see out there are basically shaped by landslides and to a lesser degree by runoff requirements. So there's hydrologic requirements that have to be there so you can pass the imposed runoff, but mostly it's all about strength. So the slopes are as steep as they can be right now, given the environmental extrema to which they've been subjected. Now, if you look at this part of the world, at about 38 degrees north latitude, 90% of the last 1.6 million years, we had about 40% more moisture per annum than we have now. And then we came out of the Little Ice Age in the late 19th century, mid to late 19th century. We saw a change in weather pattern from the rain coming throughout the year to a more concentrated period where the rain comes west of the 100th meridian. So we actually had channels like the Rio Puerco west of Albuquerque. When Santa Fe Railroad originally built over the Rio Puerco, it was only 6 feet wide back in 1881. And by 1941, the channel was 127 feet wide. And everybody was going, what happened here? We haven't done anything. Man hasn't done anything in this watershed. And what happened is, and the rain hasn't changed, the total rain, what changed was the pattern of rainfall. So you got more rainfall in a 6-month period, so your peak Qs, your peak flows, go up. That's what happens in an urbanized watershed. We see in St. Louis the peak Qs on our channels because of all the hardened surfaces and all the pipes and everything that rushes the water to the channels. We see the peak flows go up typically anywhere from 100% to 450%. So the channel has the same amount of water going through, but it has to, it's going to have a much higher volume at a given time closer to the centroid of the rainfall event. So when man goes out and slices and dices hills to make railroads or highways or any of this kind of stuff, you're playing with fire. Those slopes are all going to fail sooner or later. Now, as engineers, we hope it's later so we don't get sued in our watch. But typically, when I was a kid and they were doing Interstate 10 through the San Gabriel Valley east of L.A., the design cuts were 20 years. And then later they got to 25 years. And that seems laughable now because those cuts were made 55 years ago and they're still there. All of them have experienced problems. I don't know any cut slope in California that hasn't experienced problems. The only ones that haven't are things like US 93 and US 95 over in Arizona and Nevada and places where they don't get as much rain. But if you get rain, you concentrate runoff unnaturally, you're going to have slope problems you have to deal with. And so this is not covered very well in books at all because it's not a subject that lends itself well to theoretical research.
You can keep going.
Okay.
Just have problems with this one.
Okay. And so I'll have a lot to say on this particular subject, so I've booked out 3 weeks on it of lectures. And we're 1 week behind because of the Labor Day holiday. And I'm glad you're all here today in spite of being Columbus's birthday. Thank you. Now, problems that I'm going to want you to do. Chapter 6 problems are on pages 210 and 211. Here's the ones I'm going to want you to do. Numbers 2, 3, 4, 5, 6, and 7C and 7D. You don't have to do 7A or 7B. But that's everything except 1 and 7A and 7B. I think these are pretty good things to actually look at, especially problem number 2. Problem number 2, I really want you to look at hard and long and try to understand the significance of it, because the landed gentry of the engineering elite of Europe all watched that slide. They were monitoring it right up to the day it came down and killed 5,000 people. Okay, so monitoring and careful geologic mapping is never going to prevent a catastrophe or a tragedy. Get that out of your head right now. Just because we go over to the soils lab and we do $2 million worth of testing, that's not going to keep the building from falling down. It's what you do with that information that's critical. It's the engineering judgment you exercise. So in that case, the Italians watched the hill come down, they watched it accelerate, and they didn't issue any kind of evacuation order. They didn't get worried because they were green as grass. They had no experience dealing with something like that before. So if you're dealing with something that you've never dealt with before, for God's sakes, go get some help. Don't be too proud. Go get some help and say, should I be scared? Should I not be scared? That's the lesson we can learn out of that. Now, those 3 chief engineers, they had the highest dam in the world, Vaillant. And it was a thin arch dam. The dam did not fail. The water went 300 meters over the dam, which was 300 meters high. Imagine that. So 300-meter dam, 900 feet, and then 900 feet of water above that. That's quite a plunge pool when that comes down. And it went down the canyon and wiped out all the towns downstream at the mouth of the canyon. The 3 engineers who were the chief engineers, all structurals, they were brought up on criminal charges. They were imprisoned right away, brought up on criminal charges. One of them committed suicide. The other 2 went to prison. That's how things work in Europe, how the laws work. Yeah. So they got to blame these guys for it. The dam's still there. And there's no dam in the world had those kind of loads put on it. Dam's still there. I'm hoping to go visit it this coming spring. Okay, so look at that and realize if something's starting to accelerate, you want to start getting worried. If the movement starts accelerating, that's telling you that rupture is coming. You have a chance to run. It's like being a young Marine and hearing the mortar shell come in. The old Doppler effect. The closer it comes in, the faster you better get down in a hole, or you're not going to live to tell about it. Okay. Now, on writing assignments, let's see where we have on that. Writing assignment number 3 is what we're going to be starting on. And that assignment involves the preparation of a proposal for construction, observation, and testing services. We call in the business COT work. We don't inspect anything as engineers. We observe. And we give our observations. Inspection infers that we're approving of it and taking the responsibility for it. We don't do that. The contractor has the responsibility for the quality. We're there to be the owner's representative and say whether we think it's meeting the standards or not meeting the standards. And so I want you to look at that folder. You'll see a topographic plan. That topographic plan is the Walmart here in Rolla, the Walmart Supercenter. And it's the topography before the center was developed, taken from orthophoto aerial photos. And so you need to draw some cross sections and develop on the site plan and get an idea of how many tests you would have. Again, you look on my website and you look for a proposal that's similar. Don't look for one that's, something that isn't similar. Look for something that's a similar kind of proposal, and you're going to take that proposal and mark it up for this one. Now, this project is a lot more work than your other ones, so I'm going to give you a couple weeks to do that one. So 2 weeks from today on that one, and I expect you'll have questions for me next week on it. We will have the problems on Chapter 6 will be due a week from today, and the writing assignment 3 will be 2 weeks from today. Okay. So let's go ahead and get started. Is there any questions before I get started? Let's see, where's my... It'd be nice if I could find my... Well, I'm going to need some help finding my thumb drive here. Where?
Go to the little start menu.
On here?
And then hit computer on the right.
Down.
A little further down. Yeah. Go ahead and hit refresh. See if well, here you right click.
I don't know where the refresh is.
It said something when it initially did it. You take it. You're going to take it out and put it in again.
All right. It says green now. It just went green from being red. Does that matter? Okay. I'll take it out. It's always popped up before I've been there. Oh, there we go. Okay.
Yeah,
All right.
You didn't read it quite right.
All right. All right. Now, this is just a brief introduction. This is not an exhaustive course on landslides. I'm just going to, again, trying to tell you the things that I didn't get out of textbooks or get out of school, but that I learned through practice. This is a landslide susceptibility map of the United States. And what everybody assumes, if we look at this and we see the costs, in the United States, the costs are between $10 and $20 billion a year, averaged over a long period of time, and about 1,000 deaths a year in the circum-Pacific countries, according to Bob Schuster of the USGS. The difficult thing about looking at geohazards is they don't occur on averages at all. If you look at the averages on flood statistics in the United States prior to Katrina and after Katrina, well, the statistics are completely different because Katrina and Rita were such a big event in terms of deaths and property damage and yada, yada, yada. And so this is very difficult for governments and insurance companies to handle, because if something doesn't happen every year, it's hard to put away money for it and apportion it as a risk like you're an actuary for an insurance company. Very difficult, because these things are very spotty. They come in and they come and they go, and not with a lot of regularity. Give you an idea, they had record flooding in January 1914 in Southern California and San Diego and Yuma, Arizona, and the lower Colorado River, and all kinds of stuff. The experts said, wow, this was a 100-year frequency event. Then they had a bigger one 2 years later. And then they had another one in 36 and 38 and so on and so forth. These things tend to come in groups, actually. And so just because something hasn't happened in our lifetime doesn't mean much. Geologically, that just means that you're closer to having an infrequent event when you haven't had one for a long time. That works against the way people think. If I'm living at the beach in my beautiful home over those cliffs, and those cliffs are landslides. That's the only way you get cliffs. big, huge hunk of land just calves off and goes into the ocean. And a person will sit there, and I'll say, buddy, you need to move your house back. You're way too close to the precipice of this cliff. What do you know? I've been here 27 years. Now, to a person, that's like 27 million years. That's a long time. 27 years. Wow. 27 over 4.5 billion, the age of the Earth, is not a significant number. But anyway, they've been there 27 years, and they haven't seen any problem yet. And so they're not going to move the house. Welcome to geohazards. Nobody recognizes the problem till they live through the problem. All right, so what are some basic concepts of slope equilibrium? What are things I want you to look at? Well, first and foremost, I'd want you to be an astute observer of nature. Here we are, windows. Go out and look at windows, and you see a nice hill here, and it has a concave base, a straight slope, a convex top, and it looks like William Morris Davis's mature hill slope profile. In fact, a lot of the Ozarks looks like that, especially around my house. So that makes me sleep good at night. People with geotechnical backgrounds don't like to be in the hills because we know too much about landslides. So you see something that looks nice and smooth, you don't have as much to get worried about. That's in equilibrium. When it's out of equilibrium, it looks like a bad case of acne. It's got hummocks and pock marks all over the place. That is a slope that's out of equilibrium. There's something going on there, and it's very, very geologically youthful. We also have step topography. Everywhere we go in the world, we're going to see step topography like this in the Grand Canyon, according to how hard and how resistant and how soft various formations are. The shales are going to have more gentle slopes, and the sandstones are going to have steeper slopes. Now, you go out to California, where they got people with too much college training, and they've run around the whole place and classified slopes, and they do something called slope density. And they reason, without talking to people like us, they say, well, the steeper slopes are more dangerous. More dangerous, more prone to landslides. So if it's a steeper slope, we're going to make it red and tell you you can't build there. Now, the reality is just the opposite. The flatter slopes and the shales are the huge landslides. The steeper slopes are the more competent materials, which you'd be better off building on, but cost a lot of money to build on. So sometimes what seems intuitive, as H.L. Mencken said, there are many times where the rational, plausible explanation is dead wrong, because you haven't talked to enough people that really know about the subject. So, how do I recognize an out of equilibrium slope? Well, anytime I have cliffs, I got an out of equilibrium slope. This is active erosion going on. Don't get too close to the top with any permanent structure. Don't put your leach field and your septic tank out here, unless you want to help flush yourself down to the beach. So this is Santa Monica Beach, Santa Monica Cliffs. And what happens here is the ocean comes in the wintertime, and you have high surf, and this whole beach disappears. 25, 26, 27 feet down, millions and millions of tons of sand just disappears down to a bedrock bench. And that's when the slopes fail. And then nobody remembers that, because then as the water gets quieter, it brings the sand back in, deposits it, and all the debris from the slide is gone. Very, very efficient excavator. And voila, you're back to the cliff. So when you have a badland type topography with a very steep cliff, it comes up and it's vertical near the top, like this, that is a slope that's out of equilibrium. And that tells you that it's a slope that's experiencing slope instability problems. Okay, basic concepts of hydrology. Let's think about these. Here's some sketches that I made based on surveys that I did on a place called Radio Beacon Hill up off the East Fork, the Wind River Range up in west central Wyoming. I have a little creek down here that is the collector, and I have a very stable bedrock ridge made out of conglomerate up here. And when I measured profiles where I'm closest to the creek channel, I got this convex outward profile. And then as I got a little further back, it looked like this. Further away, it looked like this. And the furthest away here, more than double what I started with, I got the beautiful William Morris Davis shape. Now what's going on there? It's pretty easy to understand. You have the water running off the hill, and as it comes down the hill, it's accreting in area, so you get more stream power. The more tributary watershed, the more volume of water. The more volume of water, the more conservation of momentum, the more power I have to erode things. And so this comes crashing down the hill, and it meets the floodplain. The floodplain is essentially flat. And what happens here is there's a flow transition. A hydraulic jump occurs, digs a nice big hole during a big gully washer, and then it's going to have to deposit material because the velocity slows down to a very low number, so it deposits the material, but then this material has to have sufficient hydraulic grade on it to pass the runoff to the controlling base level, which is the nearest channel. This is the controlling base level. And that distance L to the controlling base level controls the shape of the slope. This is just looking at runoff controlled impacts on hill slope morphology, the shape of slopes. So if I see something like this, it comes down, and I got this fillet fill here in yellow, that's what I'm going to expect out of a slope in equilibrium. And if I move this channel further out, it's going to change this profile because I have to pass the imposed runoff and keep it moving all the way out here to the point of removal. That's the controlling base level. If I move this in, I will change this entire profile. So you want to go out and just look at what's going on naturally, because it's going to tell you all the answers. It's a lot better than expert opinions. It's better than reading books. It's better than doing anything you can do. Just go out there, spend some time, and look with your eyes. Now, what you'll often see, you'll see stuff like this on old railroad embankments, where some engineer drew it coming down here, made this sharp transition. There are no sharp transitions in geology. Only engineers' rulers draw stuff like this. What's going to happen is that's going to fill in. And that's why we call it a fillet fill. Now, if you go back and look at engineering textbooks in the 1890s, they'll show you to construct the embankment like this with a 20-foot radius transition. Never, ever, ever have a sharp transition. That's in the old textbooks from 110 years ago. It's not in any textbook I know of today. Because the people writing the textbooks today don't move dirt. They go to faculty meetings and get grants from National Science Foundation to write computer programs. Okay? They don't even know what the back end of a dozer looks like. So that's not in the books anymore. It's just common sense. Emmett, do they have a university that gives degrees in common sense yet? I don't know if that's, yeah, anyway. Now here, if you see a slope where you have a cliff, then that cliff might have a critical height, h sub c, Terzaghi tells us about back in 1943. It's a very useful little thing to know about. That's a more resistant unit. That's a slope that's out of equilibrium. And you can see this scree or talus coming down here, and then I have a sharp transition here. That's telling me, ooh, I want to be careful. I don't want to put something right here. It's going to get impacted. You don't have to be a rocket scientist to figure this stuff out. It's just a lot of common sense. Okay, so here we are. Here's our Windows picture from Microsoft. And I know right where this picture is taken, on the north side of the Livermore Valley. And that's a nice, smooth slope in equilibrium, a nice, mature slope. And nothing too bad's going on there. Now, what can disturb this are several things. We could have tectonic activity. We could have uplift of these hills. We could have erosion caused by changes in base level. That's not unusual. We've had sea level come up 360 feet in the last 11,000 years. But if we have this erosion eating down, we're going to oversteepen this slope down here. And when we oversteepen this slope sufficiently, we're going to engender some sort of slope instability. And sometimes this is due to rapid drawdown, where you have a high flow right here, and then that flow subsides, and then this comes down. Now, when you have slides, most of the time, if they're of any size, something bigger than 150 feet in either direction, there's going to be some source of moisture that's driving it. Doesn't have to be perennial. Perennial means happens, is occurring all the time. They're usually ephemeral springs, and ephemeral springs is a big college word for intermittent. That means that spring doesn't run all the time. So when you were out there checking the slope, you didn't see it. Well, because you were out there when the weather was dry. But if you went out there after 3 months of near constant drizzle, you might see an ephemeral spring, but usually they're under the ground. Usually you don't see them. What is real nice is geophysics. Use spontaneous potential, you'll find the wet spots. Because they have high conductance. So when you get a spring, here's what invariably happens. You get this one slide down here. If you have one slide, you're going to have 20 of them out there. So get that through your head. If you got one, there's probably 19 you don't know about. Because landslides are like ants. When's the last time you saw one ant living by themselves in a retirement community, huh? Ants don't do that. What do? There's always a billion of them out there. That's how slides work. Same way. So if you have a slide down here, that's going to lead to more slides. And as these slides come down, they cover up the spring. So the spring gradually builds up pore pressure till it drives another slide, and you have one coming down over another one, just like this. And you can't even count them. There gets to be so many of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then that's what the hill looks like. So when you see a hill, and it's got all these little bumps in it that look like, some German soldiers have been up here, digging trenches and stuff. Either you have very, very large moles that are very active, or you have landslides up here that are moving things around. And that is a real bad place to be parked. Now you notice you got trees up here. That's the Domagene sandstone up there, nice and stable. That's providing the water. That's where the springs are coming from. This is the Nortonville Shale, and that stuff is a geologic garbage can. It's got everything you can think of in it. It's an old turbidity channel deposit, so it's got lots of gypsum. And gypsum fouls subdrains, causes dispersion. Gypsum is your biggest enemy. You got to learn to recognize a dispersive clay when you see one, because if you try to handle a dispersive clay like a regular clay, you're going to get a lot of trouble. So you get a clay mineralogy class, you're going to go practice soil mechanics, take one. Get at least one under your belt. Dispersive clay, bad news. So this has all been graded off and repaired. See how well the repair worked? It didn't work worth a darn. It worked for about 9 years. And then this whole thing started failing because the subdrains clogged up. Other examples of hummocky topography. Sometimes the hummocks are very, very small, like these superficial ones. Typically, if we look all over the world and we say, what are the areas most prone to land slippage, it's going to be the upper 60 centimeters in bowl-shaped areas that have a pear shape, where you have an accretion of runoff increasing down in this area, and you start getting erosion, and then that erosion climbs headward because of high seepage pressures in that zone. Here's a typical cut slope failure down in Orange County, where the upper 60 centimeters to 100 centimeters has just come off the slope. And what keeps all these slopes in place is negative pore pressures. When they get saturated, they come down. They don't get saturated very often because it takes a lot of moisture over a long period of time. And what you learn about this stuff is it isn't the big storms that get on the 6 o'clock news that foment anything but debris flows. Those foment debris flows. We're going to talk about debris flows. But what's really critical for landslides is a ½ inch a day drizzle over 21 out of 30 days. That's going to put more volume of water into the ground. You start getting more than ½ inch a day, you're overwhelming the system. And so a lot of it's going to run off. So when you have a big, huge storm that comes through, dumps a lot of water, you get a lot of flooding, but it doesn't cause deep-seated landslides. That's an accretion of groundwater seepage that causes big landslides. So here's a big landslide. This is down in the Santa Paula Valley, Santa Clara River, down near Santa Paula, near Ventura, California. And we're looking at here, these are orchards, and these are avocado trees. These are full-grown trees. So this is a very large slide we're looking at here. There's a big thrust fault underneath it, And they're watering every one of these trees. They came in, graded this old slide off, not realizing it was a slide, started watering the trees, and they got to give them about 44 inches of water a year to get them through the dry season in California to grow avocados. And what happened is they had 3 years of extra normal rainfall between 66 and 69. In fact, they had a 100-year, 30-day period in January 69, and everybody went, oh man, we got through the 100-year, 30-day storm. And then in February they had a 75-year. That's what can happen. That's how dice roll. Go to Vegas if you don't believe me. You know, roll a 7. Can you roll a 7 twice? Sure. Yeah, you can. Lots of people are unlucky. So what happens here is this got sufficient moisture that the whole mountain just started coming apart and moving. And when you look back on the aerial photographs, what you see is gigantic hummocky structure up and down this entire valley. That's all structurally controlled by that blind thrusting coming up, because the blind thrust perches the groundwater. Blind thrusts are very, very problematic with large slides. Okay, colluvial-filled bedrock ravines. Here in Missouri, what we have lots of are ticks, chiggers, and colluvial-filled bedrock hollows. They're just everywhere. We're on the oldest erosional surface in North America here. We can go over near here, Fort Wood. We go up here to Rolla Vichy Airport. That surface there where they built that airport back in World War II is late Miocene erosional surface. There's no other late Miocene erosional surface in North America. Now, are there older erosional surfaces out there? Yeah. Western Australia, you go back to the Cretaceous. Those are really old. So around here, back to about 15 million years. Western Australia, go back 75 million years. But what we have going on is water tends to travel down the fall line of the slopes, and you get colluvium and alluvium filling in valleys and pockets. The alluvium is up on the hills. The colluvium is up on the hills. It is gravity-borne debris, and the water-transported debris, alluvium, is down in the active channels. And everybody always looks and learns about alluvium in school because that's groundwater aquifers, typically alluvium, but they don't learn much about colluvium. Now, if you actually look here, the water table is deepest, typically, underneath a bedrock ridge, under knob. And as we approach the channel down here, the groundwater gets closer and closer to the ground surface. And we really see this obeyed all over the loess-covered, dissected uplands of Missouri, especially around St. Louis area. You want to look at a groundwater map that my postdoc, Jaewon Chung, has done. We've been comparing it with all the borings everybody does all over St. Louis, and we're always within a meter, just using a theoretical model which has a good topographic coverage, digital elevation model. What are this common geomorphic feature? This colluvial-filled ravine is usually pear-shaped, like you see here, and in this case, we call them zero-order basins if we don't see a defined bed and bank. If we don't see a channel coming up here, which neither one of these has, then that's a zero-order basin. This is fluvial geomorphology lingo. And the first time you get a channel down here underneath these redwood trees, that first channel is a first-order channel. And the one it runs into is a second-order channel, which runs into a third-order channel, and so on. Each one with increasing level of stream power. And so ability to react to environmental change. Well, here is a zero-order basin right here. And you see the start of something of a channel up to about here. And we have exposed bedrock right here where we've had a big storm come through. And that storm actually took the soil regolith off about 0.5 meter to 1 meter thick. And you can actually see there's the regolith sliding down, very, very steep. These are steep areas. And then we can see all this debris piled up down here, about 10,000 yards of it coming into these trees. Now, you go 10,000 yards in this one little corridor? Yeah, that's how it works. You see you got a big area here, and all that is focusing down to this one little neck right there. So if you're a pioneer, this is where you build your house because this is where the springs are. But the pioneers were never stupid enough to build right in the channel. They always built off to the side one way or another. So when you do have a flood or a debris flow come down, you don't get killed in the middle of the night. So always remember that one. If you have to be on the channel, build a bridge so the debris flow goes under you. That's what they do in Europe. But this is a good example of how, here's where the down cutting is occurring. You go to the Grand Canyon, this is what it looks like. All the down cutting is occurring in the steep side canyons in the head amphitheaters of the steep side canyons, and then the material is carried down to the Colorado River in debris flows, and all the Colorado River does is take out the small grain stuff like a conveyor belt. Colorado River is not cutting the Grand Canyon. It's the head walls of the steep side canyons is where all the cutting is going on. Fantastic levels of cutting going on. All right, if we go out and we get out our binoculars and we just start looking, that's why it's good to be a bird watcher. You learn how to sit there and be patient and just watch nature. What you start seeing are some real interesting patterns. Where you see these lines, those are resistant beds dipping back into the slope. Where you see this smooth area, that's colluvium. Look at the demarcation right there. So I got bedrock rib, here's the colluvium line. This is all colluvium. There's the colluvium line coming up like this, goes all the way up here, comes around, bedrock rib, colluvium, bedrock rib, colluvium. So you see here is about every 100 meters, you got a colluvial-filled ravine. And down here, there's down cutting occurring on this trunk channel. That's the first order trunk channel. There's no channels here yet. And you can see the erosion, recent slumps that are occurring right here in the colluvium, because water is coming up underneath the colluvium and really literally lifting it off the slope. Now you can really see these things if you look at road cuts. Here's California Route 1, the coast highway where they love to film all the car and truck commercials and things. And this is a series of bedded cherts right here. And if you look on top, you see a slight depression here, about 6 feet in difference between here and there. 6 feet, 72 inches, not much. Now, they cut this slope out back in the 1930s with a steam shovel. Now what you see here is the bedrock colluvium contact, watch this, comes down, 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 dives right here, 17 feet below the ground surface, and then comes back up. I've got a very well-developed argillic B horizon right there, a little bit immature, a nice A horizon, and I got all kinds of water-loving plants right here. Can't imagine why. That's where the seepage. There's a permeability contrast right here between this soil-type stuff. This is just loose, loosey-goosey fill, natural fill, not man-made fill. And you got this Miocene age and older bedrock down here, Eocene age. And so you have a permeability contrast here. So that's where you would need to put a subdrain if you really wanted this slope to survive in the long term. So if we look at cartoons, this is kind of the picture we have. We have a system where sometime back in the Pleistocene, during the Ice Ages, there was more water, more stream power than there was landsliding. Landsliding couldn't keep up. There was so much water, it's just cleaning everything out. It's like taking a fire hose up there and just running the fire hose all afternoon. All the soft material gets washed out, and it leaves this bedrock hollow. And what happens is, as we came into the Holocene, starting about 14,000 years ago, we start seeing these things fill in because the amount of rainfall lessened and the climate became more temperate. And so this thing slowly fills in with big stuff down on the bottom, root balls from big trees falling over, you have animals burrowing in, you have rainfall hitting the sides of the hill, you have animals kicking stuff in as they run out of here. So it slowly fills in till it looks like this today. And my father was a real expert on these things. He would go out to build a house for somebody. And of course, back in those days, like around here today, you didn't have sewer systems. You had to find some spot that wasn't bedrock where you could build a septic tank or a leach field. And Dad had a long steel probe. It was about half an inch in diameter and about that high, and had a handle on it that he had welded onto it. And he'd take this probe and go along and probe along. But it didn't take him too long to figure out where these hollows were by looking at the girths on the trees. Because the girths on the trees, over here, when you have 30 inches of soil, you get a pretty squirrely tree. But when you get out here on a colluvial-filled bedrock ravine, which has very slight topographic expression, you see big, huge girths on black oak, white oak, pin oaks. And Dad would know, oh, this is a good place. And he'd probe there and push the probe all the way down, never hit bedrock. And didn't cost him $10,000 to bring Shannon and Wilson out, do some trenching to tell him where to put the leach field. Put the leach field right there. And so that pretty much works anywhere you go around here. You'll see that same kind of a system. If we look at these ravines, they're never symmetrical. So get that out of your brain right away. When I was taking all these classes in civil engineering, one thing I can say, looking back on all that, I took every class they had at Berkeley. I got 400 units. And oversimplify, they oversimplified everything. I had no idea when I went out and practiced how unsymmetrical and how complicated things really were. I was really overconfident. And here's the actual case where you look at a hill, they're never flat lying, they're always got some inclination. Got a colluvial filled ravine up here with very coarse material. Then I got a bedrock high here, got another one down here, but this one has more finer grain material because it's further down the slope. And then back here I got another one, but it's back over here, and it's not nearly as steep over here on the dip slope side. This is called the obsequent slope, or the anti-dip slide. The obsequent slide actually produces more colluvium. Steeper. Right here is a case I had for City of Oakland where we had a culvert right here, and the culvert came down the hill about 150 feet and discharged right about here. And in one storm, January 3-5, 1982, this culvert dug a hole down here 47 feet deep, much to everybody's shock, including me. And we went out and started drilling on this thing and probing around, and what we found was we had a huge colluvial-filled bedrock ravine in here, and the phi angle of this material was all 45 degrees. That's gorgeous, clean, hard chert. It's rock. No cohesion. So if you run water on it out of a culvert, it just erodes like crazy. You get this beautiful vertical hole 47 feet deep. And of course, if you look at the trees now, go back and use my dad's methodology, look at the stunted growth on these guys. They're on the bedrock. There's the highway. Come over on the fill. This is the side cast fill for the highway, put in 1935. And I got pretty nice trees. Trees are getting smaller, smaller. Now watch as we go down the hill. Trees getting bigger, bigger, real big. Why are these trees really big down here? Because the water is traveling through this ravine, and that's where the water gets closer to the ground surface. So you got to learn. Botany is your friend. Learn as much about it as you can. In fact, one thing I had to learn about college is everything you learn, you're going to use somewhere. You just can't see that yet. But the more diversity you get in your background, the more it's going to pay dividends. And I learned to become a very astute observer of the trees working in the Bay Area. Now, permeability. Permeability is a colloquial term. If you want to be college-like, we call it hydraulic conductivity, because it's the permeability with respect to water. But I'm just going to use the old term, permeability. You know what I'm talking about. I'm not talking about petroleum engineering. Okay? We're talking about water. All right? If we look here in this zone of aeration, where we have the fractured, weathered bedrock, the bedrock creep zone, that's where most of the water water moves through that's young water. If I take a has-waste site or some dump somewhere and I start drilling down deeper and looking at isotopes, I'll find the water down deeper is older water. It's not moving around. It doesn't have nearly as much oxygen in it as this stuff up here near the surface. So I've got water that's percolating into open fractures right here, and then it's moving pretty rapidly one way or to another. Now, I have increased head right here. So this actually pushes this water like this, and it gets down here first, actually before that water gets there. So you do have to think about it three-dimensionally. Now, in school, we always draw two-dimensional pictures like this. But in the real world, it's very three-dimensional. So when I'm pushing water down right here, it's not moving in this plane. It's actually moving towards you. So it's going that way, but it's also going downstream because of the influence of the other water right here that's moving downstream. So the weathered zone lying beneath the topsoil, so here's the topsoil, the weathered zone between the topsoil and the zone of permanent saturation, the groundwater table, that's generally dilated due to slope creep. Slope creep is strain under sustained load. So this is slowly tilting over, tilting over, tilting over. It's opened up, it's dilated. If this clay has desiccation fractures, the water's going to get down into here very quick and move around. You really see that at the beginning of the season. If you have a real large storm at the beginning of a wet season, most of the water goes into the ground, into the desiccation fractures and into all the open fractures. If you have that same storm hit at the end of the wet season, you'll get a record flood because you have high runoff coefficient, because after you've taken all this water in, the desiccation cracks swell closed. So now when additional rain comes, it just sheets off as runoff. So the runoff you get depends on the 60-day antecedent moisture. Now, colluvium has been modeled by a number of people. This is Russ Campbell's model, and this is the one that I was raised on. It's wrong, but it still has some great things to learn on it. Let's go to school on it. What Russ was working on the debris flows. He's a USGS scientist. He was working on the debris flows at Wrightwood up in San Bernardino County, which were very destructive. They had a number of debris flows that wiped out half the town. 1941, 1952, 1969, 1978. And so they sent Russ up there. And one of the things he learned was the colluvium had a lot of strength. There's your strength plot, 45 degrees. But notice, no cohesion. Zero cohesion. And if it had been here a long time, you have an immature argillic B, and you got an A horizon up here, and that sheds a lot of the runoff, and the root strength in here helps you until that gets broken. If that gets broken somewhere, then that water can get in much easier. But we also have water that comes through this zone and feeds up into it. In Russ's model, he assumed that the water was down in here, the low line, and traveling through the colluvium, and he reasoned that the colluvium was more pervious than the bedrock. And that's not always true. It's usually the bedrock, the weathered zone in the bedrock, that's more pervious than the colluvium. But they didn't know that then, because we didn't have these sites instrumented with continuously reading potentiometers. That all came about because of the environmental revolution in the mid-'80s, when we started monitoring all the landfills out there with hundreds and hundreds of thousands of dollars of instrumentation. We started learning a lot from those. What happens here, he's reasoning is, well, it's down here, we're not going to have a problem, but when the water gets up to here, I have very high uplift, that lowers the effective stress, and this whole thing comes unglued and goes streaking down the hill, especially when it gets disturbed. Well, we can actually see this kind of effect when we go out and look. Here's a site that I had in very clayey material with thousands upon thousands of roots extending down several meters, which were unable to hold this thing here. The water pressure here was so great, the hill just blew out and disappeared. So you have a rooting zone that really engenders a nice protective covering on your colluvial-filled ravine. If you break through this zone, you're in big doo-doo. Now this zone, by the way, is very hard to sample with drive samplers. When you're drive sampling in that rooted zone, you're going to densify the sample. So you better mark the barrel, say, mark, I did 19 inches. Okay? You pull the barrel out, you open it up, you measure, you're going to have 16. Yeah, you just densified it 3 inches. You're always going to densify when you do a drive sample and you're pounding a donut on it. And it lies like the devil in the upper 2 meters. Be real careful, because that's the critical zone you want to assess strength on, and it's usually not as strong as you think. Now, if you push a Shelby through it nice and softly, you'll get a better results. But no, people don't want to do that. It costs a lot more money. All right. So topographic expression, I came to the conclusion that topographic expression was my best indicator to tell me how active things were. I can see here I got activity down here very, very clearly. The activity's all in the low area. If I look at a topographic plan of something like this, it's going to look like that. And if I see these little guys right here, if I see an active erosion going on, I know this ravine is quite active. This one is not active. That's like these right here. This one, the colluvium's gone. There's been activity in here, but you have a nice V-shaped. There's not going to be a lot of colluvium sitting in here. So what you end up having are 3 distinct cases. The active landsliding situation on the left, the dormant, no sliding occurring yet in the middle, and the sliding already occurred here situation on the right, and you're going to have a first-order channel going up right here. So the case you see right here corresponds to this one, the number 2. I'll show you some others. This is one I had in the city of Vallejo, where they had a series of storms in 1986. They had a very heavy month in the middle of the month, 86, and they had a series of failures that just suddenly lashed out and occurred right here, right above a brand new subdivision, scaring the people considerably, as you might expect. And then you look back up here in the higher hills, no problems. These are much higher, got more rainfall, but when you went up here and looked at these were bedrock ravines. All the colluvium had long ago been taken out of there. The larger the watershed, the faster it will respond to environmental change. The smaller the watershed, these are tiny watersheds right here. The smaller the watershed, the much longer it will take. So this watersheds were so small right here, they hadn't even reacted yet to the Pleistocene-Holocene transition that started 14,000 years ago. But these were 10 times, 20 times as big. All the colluvium had been debauched out of them long time ago, a couple thousand years ago. All right. Now, trigger mechanisms for debris flows. I'm back to my colluvial-filled ravine. How is it shaped? It's typically shaped like a spoon or like a pear. A pear is fatter in the upper part and thinner on the lower part, but it has a spoon shape. It has a definite 3-dimensional shape. If I do a cross-section right through the middle of this thing, where it's maximum thickness, it's going to look something like this. This is real world. Now, what I want you to see here are several things. One, the seepage is going to occur in the bedrock creep zone underneath the colluvium. So the water's going in over here on the bedrock ribs. It's percolating into the ground, and then it's following these arrows. It's accreting towards the axis of the colluvial-filled bedrock ravine, and it's building up underneath. And what happens is you get bedrock high points and bedrock low points. Where the colluvium's thicker, you can develop high uplift pressures because of these pinch outs by these resistant materials. And typically the blowout, the initial blowout that kills everybody, will occur right here where the pinching is most severe. because of the accretion is most severe at that location. So if I just put a trench subdrain right there, a little big trench subdrain, 50 feet long, backfill it with rock, that's the end of that. That's how easy it is to fix. So I've had the Forest Service doing these kinds of repairs since 1984, and it's the primary approach that the Forest Service uses all over the western United States. Because just you can put in the trench drain right here cheaper than one phone call to Shannon and Wilson. So you might as well just go out and do it, because you have plenty of rock, and you just want to get some drainage in there so that you alleviate high pore pressures building up. And you'll figure it out pretty quick when you put those in, because you'll hit water at very shallow depth when you go in there and dig around with the backhoe. So that's a real good picture. Bedrock spur on the side is where the water goes into the ground. Colluvial-filled bedrock depression is what gets lifted up by these pore pressures that develop through the accretion of shallow groundwater seepage. So the biggest thing we worry about are emergent seepage forces. We have seepage coming down, hitting something that's more resistant to flow down here. You're going to have emergent seepage forces. And you'll see things like water-loving plants right here. You see cattails and all kinds of stuff that loves water. There's that botany again. That's a dead giveaway. If you see a bunch of water-loving plants right here, and you don't see them right over there and right over there, do some thinking. Ask yourself, why are they here and they're not over there and not over there? There's a real good reason for it. It's the accretion of subsurface flow. If it was structurally controlled, you'd see it all the way up and down the valley. And that does happen with thrust faults. You'll get springs all the way along a valley because the thrust fault runs all the way along the valley. That's very common. Also, you can have these pockets where things are deeper. If the colluvium's deeper, you'll tend to get pockets of water in here with higher pore pressure. And this will drive you nuts, because you'll drill a hole right here, and I had this happen to me in Hawaii many times, where I drilled a hole here and the water came shooting up 5 feet out of the ground, and I was in pure clay. Now, you never want to tell a soil mechanics professor that, because they'll sit there all day long and say, that's impossible. Clay doesn't produce water. That's impossible. Clay can't produce water. That's impossible. Clay can't produce water. Thank you, Herman. Go out and drill some holes now. Clay that has excess pore pressures, clay is wonderful for trapping pore pressures. That's what it's good at. And how long do these pore pressures last? A couple minutes, a couple hours. You know, I had one in Hawaii where I had an active slide, pure clay. I drilled into it and lifted everything out of the hole. Lifted our drill rod out of the hole, everything, and we measured 66 inches coming up right here, right in my eyeball level. Water just pouring out. We thought we had hit a fire main. But it went down rapidly. And within 3.5 hours, it was just dribbling out of the hole. And by the next day, there was nothing coming out of the hole. What we had done is, we had tapped the slide plane, the basal slide plane, and there was trapped pore water in that basal slide plane, and we alleviated the pore pressure through putting in a subdrain of sorts, the borehole. You also have these kind of situations where you have a change in slope, like at the base of a fill slope, and the water will come up to the ground surface or near the ground surface. And you have this case where you have a change, where you have a unit that's pervious that's pinching out. And again, this is like a fill on a bedrock. This is the most common one. This one and that one are the two most common ones I ran into all the time. This one was easiest because I'd see the foliage here. That was the dead giveaway, what was going on. This one, where I had the big highway embankment or a dam or something down here or a levee, this one's tougher because I only see this problem under limited conditions, where I have the high pore pressure down here. And then you'll see starting to pipe down here. So if you're not out there when the action's occurring, you'll miss that one. All right, real data. Here's some real data on a colluvial-filled bedrock ravine. And this is the bedrock rib in Pacifica, right next to, this is a ravine that failed and killed a bunch of children, called the Velez children, in the January 5, 82 storm. And we instrumented it a couple years later. And what we're seeing here is very high pore pressure response very quickly in a early midwinter storm, goes up 9 feet, and then tails off pretty quickly. Now, this is 200 feet away in the center of the colluvial-filled ravine. Look at the pore pressure response. Because this is fractured bedrock. This is clayey, silty colluvium over the fractured bedrock. We see the pore pressure coming up at half the rate, coming up higher, up to about 12 feet, and then topping off. It's just can't drain. It's got all the water it can hold, and now it's just pushing that water slowly out of the hill. It's like a constipated hill. And it comes here, and this thing is sky high for a month and a half or two, and then it slowly starts to drain. That's the permeability contrast between those materials. That's the feeder, that's the killer. If you put a subdrain in here, you take care of the problem. Now here I am, I'm modeling it with finite elements here. Classic spoon-shaped depression. The low line is the two-dimensional model, which everybody starts with. And notice where I'm getting the accretion of pore pressure. Right down here where the pinching's occurring. Ha! Big surprise. That's where the pinching's occurring. Now, if I model it three-dimensional, look at what a difference it makes. I double the pore pressures by modeling it as it really is in 3 dimensions. So this is where the value of finite elements. I used to make lots of jokes about finite elements because I did my PhD thesis on them, and I could get any answer you wanted. I'd be like the geophysicist, and I'd turn to my client and say, "What answer do you want? I'll get it for you." Because I would get different answers all the time. It's very valuable to run parametric analyses and run it up to the point where you go plastic. It doesn't model plastic behavior. And guess what happens in soil mechanics? Only things people are going to hire you for is when you get plastic behavior and something goes bump in the night. They're not going to hire you to tell them about the elastic things that don't hurt anybody. I mean, voila. That's easy stuff. But finite elements are good for seeing stress concentrations, strain concentrations, seepage concentrations. They're telling you, here's where I need the subdrainage. I don't need it up here. I don't need it down there. I need it right there. That's where I need the subdrainage. And that saves my client a lot of money. If I can say, right there's the sweet spot. Put it in right there. Don't you wish you could do that all the time? Now, that's a lot easier said than done. Here's what happens when you don't have pore pressure relief. You have people call you who don't know any soil mechanics professors, so they don't know this is impossible, and they say, "The clay on my slope exploded last night. It just vomited onto the hill." And you're sitting there listening with your PhD going, "Oh, I'm sorry, man, but clay can't do that. Clay doesn't vomit, and clay doesn't have explosive, fluid-like behavior." "Well, you come out here, you ass, and you look at it yourself, and you tell me what's going on." That's what this one lady told me right here. And she even called me a name. And when I got out there, I saw that I deserved the name. Because there it was. Does that look like vomit on the hill? Pretty much. If you're a frat boy, you're shaking your head going, "Yep, that's what it looks like, Dave." It looked pretty much like that. And I'm sitting there just going, how can this happen? Clay is not supposed to do this. My soil mechanics professor said it couldn't happen. And once again, you see right here, you go up here, what's going on? There's a little fault running through here, and you got pore pressures build up. And you had pore pressure relief, very sudden pore pressure relief. Same thing up here. This is all clay. And this thing had such high fluid pressure, when it blew out, this is clay trains coming down here on a 2% grade. That's impossible. That's impossible. Watch out for what's possible and impossible. Nothing's impossible in the real world, only in your PhD orals. So, and you tell them what they want to hear in their PhD orals. Don't tell them stuff I tell you, okay? But right here, you can see that had a lot of fluid pressure to go flowing over the grass and deposit clay on that flat of a slope. That's pore pressures. So pore pressures are very real. Well, what are some physical attributes of debris flows we need to appreciate? If we look at topographic expression debris flows are actually very, very easy to identify. You just have to look for a few key things. You look at the fall line of the slope, and you're looking for disturbances that are not continuous all the way up and down the valley. So if you're seeing something here where all of a sudden you have this lobe, this depositional lobe down here, and you go up the fall line and you see evacuation on the same fall line that you have the accretion, you go 1 and 1 makes 2 last time I checked. That's a slide. There's some kind of mass movement going on here between right there and right here. There's something going on. So how would I map that? There's how I would map it. Now notice, there's never any such thing as one lobe. If you found one lobe, you just aren't really good at mapping yet. If there's one there, there's going to be more. Here's a previous one right here. And the one that you see that's the easiest to see is just the latest one. That's just the latest one. So right here, you know right away, ouch, I got to be careful with what I put across here. And of course, this is the lobe. This is always where they had the highway down here, and they wanted to put the highway there, and I'd say to them, just put the highway around this. Oh no, Dave, we can't do that. We'd have to buy extra property to do that. We have to figure out some way of putting the road across here, right through the slide. And well, there's all kinds of things you can do. They all cost money, however. Now, if you look at this one, here's a whole series of debris flows that came out of an area that had never had debris flows previously in Woodland Hills back in 1982, 83. And these, actually this is 1978. This actually occurred in early March 78. And these came down and they deposited themselves when the grade hit about 10%. Right around 11% grade, that's where these things will come down, no shear strength, they behave as fluids, and then they'll coalesce and bleed off pore pressure and gain shear strength and suddenly stop. Just like epoxy setting up, or like concrete setting up. And it'll be right on the 10% grade area. That's right where everybody likes to build houses. See the houses going in right there? That's right where everybody likes to build houses, especially around Phoenix. If we go up and look at these erosive cycles, they're very, very frightening. Here's some up above Muir Woods National Monument in Marin County. These basins, these colluvial-filled ravines, didn't have any kind of failure until 1967, January 67. They started evacuating at that time down here low, and each decade, every 8 to 15 years, they've had a significant event. Now, a significant event, this one in 1986 spewed 30,000 cubic meters of material. It doesn't look that big. 30,000 cubic meters came out of that one in one event over Thanksgiving weekend. So these are all subject to external and environmental factors triggering them. This is one over in the East Bay, Contra Costa County, where they just had an intense rainstorm. And again, the upper 40 centimeters just peeling off. And then down here it accretes, and the flow comes down onto the building pads and does all sorts of damage. Here's the one over in Marin County. We're actually standing in it here. This is Professor Rob Olshansky. He's now at Chair of Environmental Planning at Illinois, at Champaign-Urbana. He's standing on an old erosional surface, that old erosional surface right there. We found these older erosional surfaces down in here, and this one he's standing on is about 6,700 BP, so 6,700 years ago, about a third of this ravine came out. And then it redeposited itself and filled in. And this event that occurred in 86 had eaten way down below that, all the way down into here, and was taking the whole thing out. And we were very, very curious as to, what is the trigger that suddenly causes this thing to go into what we call a debauching cycle. It's just, this debris is just coming out of here like crazy because there's no cohesion here. So if you put concentrated flow in here, and there's no man activity going on up here other than grazing, and grazing does have an impact on runoff. And so if we start looking at these things in section view, in 82 in Marin County, not too far from that site, we had a series of debris flows that came down and killed a bunch of people. So, of course, when you kill a bunch of people, there's all sorts of attorneys get involved, and the attorneys say, what's going on here? And the city wants to know, well, should we have let people build in here? And the answer was, well, you can build in this deposition zone between 6 and 11% grade. That's where everybody wants to build, by the way. Up here, you're getting a little too steep. It gets much harder to build the structures up in there. And this is where everybody wants to build, but that's where the debris flow deposits itself. Because you go to alluvial flow down here at 1.5% grade. So here we had gravel in the channel, so we have alluvial conditions to right here. So that's where your school training stops. Then we had a clean bedrock channel up to 6%. And then between 6% and 10 and 11, we had debris, very active debris. So we went in here and actually trenched. And when I trenched that area, it was incredible. There was just one debris flow over another, hundreds of them. And they were anywhere from 2 inches thick per event to, I think the maximum we got was 19 inches. One event. Just one stacked over another one, over another one, over another one, over another one. And so they were asking me, well, it's unsafe to build here then. I said, no, you could build here. You just have to put a dam right here, a debris dam, and catch the debris and keep it from coming on to that fan. Well, a lot of people didn't want to hear that, but that was the engineered solution. You also have traction forces. If we actually look at a debris flow coming out of a steep bed, they come out of steep bedrock channels. Here's the transition at Big Thompson. This was the deadliest debris flow in American history. Killed 177 people, 178 people, 1976. Here's where it transitioned out of the bedrock channel, coming into the wider valley. Tremendous traction. It's snowballing and just picking up more and more material. We're going to talk about why that is. This is Wrightwood, the one that Russ Campbell worked on, 78. Same thing. These both had mica schist source areas. Mica schist is your worst material because mica doesn't dissipate pore pressures. Mica sits here like this, gets into a flow, and the water can't get out because of all these little flat platelets holding the pore pressure down. So mica schist is your worst material for fomenting debris flows that have long run out because they don't dissipate pore pressures easily. Well, destructive snouts. The Japanese have done a lot of great research on this, and so has Sue Cannon at the USGS in Golden, Colorado. She has a team that goes around and looks at fire flood sequences and debris flows. And the snouts can be very, very destructive because all the rocks tend to collect. The big, huge boulders tend to collect in these things, and they knock things over. Here we are flying by in a Navy airplane one weekend after some storms in Northern California, and I see this thing just coming right out of the forest with this gray color depositing itself over the orange-colored terrace deposits. That's just a recent debris flow that's just come along there and buried the road that was along there. This is the one in Woodland Hills where they built these A-walls to deflect the debris flows, and those worked a few years later. And they deflected the debris flows around those houses into some other houses that were across the street. So when you design something like that, you got to think about where are you going to store the debris. Now, if we go out and look at slopes on these snouts, we'll find they have a very high angle. This is out in Death Valley on Artist Drive, Artist Palette Fan. Very high snout angles, 33, 34, 37 degrees, not uncommon. And also, if you trench through a debris flow, you'll see inverse sorting. This is really bizarre. Inverse sorting. What does that mean? That means the big stuff on the top, the small stuff on the bottom. That, and it's matrix supported. Down here you see regular channel deposits. Channel deposits are easy to recognize because they'll have imbricate pebbles, and everything is hydraulically sorted. Everything's the same size within each different flow regimen. When you get a debris flow, you get everything. It is mixed master junk and lots of subangular and angular fragments. But you tend to get these bigger boulders that get floated up through high uplift because this is not water, this is a slurry. So Archimedes' principle is much more in effect here. That boulder weighs its dry weight minus the weight of the fluid or the slurry that it's in. Well, that slurry is not 62.4 pounds per cubic foot. That slurry is closer to 90. It's like concrete coming down, like wet concrete coming down. And so this boulder doesn't weigh anything close to its dry weight. It may weigh 10 or 20% of its dry weight. So it just gets picked up and lifted up through uplift. It's just effective stress. Now what happens to these things long term when you're in dry areas like Arizona, Nevada, New Mexico is these flows come down like this one right here, which occurred in 1976 on Artist Pallet and Fan. It actually buried the road in 3 to 17 feet of debris. And they gave up and just built a new road, had to pave a new road. There's no way you could dig the road out and you're 17 feet down. And what happens is when you monitor it over the years is subsequent runoff comes down through here and sluices out the fines. And as you sluice out the fines, you get this nice desert pavement. You get a nice rocky surface right on the top, which is kind of a protective sort of surface. But when it's first deposited, it's very fine grained, lots of little gravel. This is all 3/4, 1 inch gravel type stuff, pretty small. But this gets deflated and pressed down. And when you go out around Phoenix and you walk on the fans, if you trench the fans, they all look like this. What all the fans look like that I've trenched in Arizona and Eastern California around Palm Springs. Here's one that I did in Palm Springs area. Nobody liked this, so I didn't get any more consultations there. I got asked by Riverside County, Rogers, we got these guys that want to build up here. These Hollywood people want to build beautiful homes up here on the Fan, and this is a desert. Is there any problem here with rockfall crashing into them? I said, well, you can always have rock falls, but when I look at the air photos, there's your debris flows that you've had in the previous 100 years. Some just beautiful debris flow fans come out of these little first order and second order drainages. And of course, these people didn't like me very much because I was saying, well, put your parking area up in here, but put your houses down here. Or if you want to put your house up here, you got to put big, huge impact wall behind it, like 3 foot thick reinforced concrete and earth sheltering and blah, blah, blah. And anyway, they found another consultant who was able to say that I was being overly conservative because I didn't know the actual ages of these things. And these are probably from the wetter climes of the Pleistocene. And he didn't think there was any problem there. Give me $500, please. So that's, but you got to realize that some people will say anything for $500. But I'm not one of them. All right, let's take a little break right there. Take a real quick break. Head to the restroom. And then we'll get back starting in about 4 minutes. back on. Basic mechanics of debris flows. Debris flows are particularly vexing because the people that get killed by them down here often don't even feel the rainfall that causes the debris flow. So they're operating under the assumption that everything's fine. It may be raining at some higher elevation, but they don't get too concerned about it. And so what happens here is this orographic lifting. Whether you're in Japan or coastal California, Washington, Oregon, anywhere where you have prevailing wind and you hit a mountain front, as that mountain front rises up, that rainfall can be retained if the lift rate is above 13 feet per second. Because 13 feet per second is the average rate of rainfall. 27 feet per second is the theoretical rainfall rate, but the rain actually has Brownian motion as it goes down, and so it actually falls at an effective rate of about 13 feet per second. So if this is rising at greater than 13 feet per second, it retains the rain until it senses that it's going to go over the top of the mountain range. So right about here, right about the 80% of the way up, right there, it just suddenly drops all this retained water. Now, we first got a hint of that back in January 1943 at a place above Santa Anita Canyon called Hoagie's Camp. Hoagie's Camp was back over here. It wasn't even up on the top of the ridge. It was back here. And Hoagie's Camp recorded, they had a continuous recording rain gauge there, operated by the Forest Service, and they got 1.26 inches in 1 minute. And a lot of people from the Midwest and the East, professors again, of course, civil engineering professors, hydrologists, said, that's impossible, because we haven't seen that in Vermont or New Jersey. Well, they don't have mountains in Vermont or in New Jersey that are like these kind of mountains that go up 8, 10, 12,000 feet high. And so, no, they hadn't seen things like that. Turns out the numbers you can get up in this zone are really astronomical. And you get a lot of water in a short period of time. That water is going to accrete and come down this thing, and you're going to get debris flows and debris torrents. And they're very, very destructive because they have large class. So people aren't going to be able to float in them with life preservers or anything like that. What typically peels off in these kind of things is the soil regolith. So the upper, again, the upper 40 centimeters to 2 meters can just come peeling off these slopes and accrete coming down. Here's your big pear-shaped basin, and you see that all coming down into this one thin little chute here, and that chute is going to send all that debris into this house. And it can have a tremendous impact on the house. So it's a matter of severe rainfall intensity and duration. You have to have both. You have to have intensity, inches per hour, and duration, so many hours. And the threshold for every place is different, depending on what the normal pattern is there. There's places on Kauai, out in Hawaii, where they get over 400 inches of rain a year, where their debris flow threshold is sky high compared to what it is in Los Angeles County, for instance. So debris flows also tend to favor shaded slopes. So if we look at most of North America, we'll find that we have shaded slopes on the north side, and we tend to get more barren grasslands on the south-facing slopes, where we have more afternoon sunshine and maybe a little more wind, if the prevailing wind's coming from the south or the west, and which is what we have around here. And so you tend to get more debris flows coming out of this zone over here because there's more moisture retention. So that heightens the antecedent moisture level. The higher the antecedent moisture, the higher the runoff coefficient. The higher the runoff coefficient, more water you got. The more water you got, the more stream power. The more stream power you have, more erosion to break through that A and B horizon, which has the rooted reinforcement. Once you break through that into the regular colluvium with no cohesion, whoa, you just pull that stuff right on in. You're just like a football player, eating hot dogs. You just go gobble all that stuff up, and away you go. So here is a typical threshold line. And this particular one is for Contra Costa County, which is in the San Francisco East Bay, place that has average rainfall amounts between 14 and 28 inches a year, mostly in a 6-month period. And so what the USGS has done here is they've come up with a empirically derived threshold line. And the line over in the Coast Ranges is much higher. In the Santa Cruz Mountains, the line's way up here. But over here, where it's a lot drier, that's their threshold line. So what that threshold line is saying is if I have more than 0.5 inches per hour for at least 6 hours, I'm going to be on that side of the threshold. Or if I have 0.3 inches per hour for at least 8 hours, I'm going to be over that line. Or if I have 0.2 inches per hour for 20 continuous hours, I'm going to be over the threshold line. So the 60-day antecedent moisture is a key factor, and then this is the trigger factor in the near term. So this is what Sue Cannon does. She'll go out, the Forest Service will have her come out after they have these fires and stuff, and they'll say, well, when do we need to be worried? She'll just pull out one of these things and say, well, here's the curve for that range down there, here's the data curve for this one over here, and you're probably something right about there. So you got something to work with. And you know that, okay, if we have a national weather forecast that we're going to have an intense storm cell coming in there, we maybe need to be worried. Now, in reality, what drives these things are high-pressure cells. What's a high-pressure cell? Well, you have all this wet moisture kind of smoking along. You ready? We're going to kind of smoking along, and all of a sudden, and it's blowing onto the continent, and all of a sudden, right here, over the hot desert, or over the big Central Valley, there's a big high-pressure zone because of radiation heat. This warmed up today. And so you got this hot air rising. Well, this cold, moist air, cooler, moist air, it's warm too. It comes in, hits the high pressure zone, and stops. It's just like an end sweep, you hit the wall. It hits the wall, and it can't go, so now that rain just keeps falling. And that's how you get these long durations, like 21 hours. Because average storm duration, continental United States, 90 minutes, 1.5 hours, and that's about what it is around here. If you don't have your umbrella with you, see, I borrowed one. You can always just hang around for an hour and a half, and chances are you can probably walk to your car and not get wet. So that's the average storm duration. So half the time you're going to be longer than that, half the time you're going to be shorter than that. That's average duration. Now, to get 21 hours or 35 hours, that's what happened to the Bay Area, January 3-5, 1982. They had a 36-hour duration storm. That's why they had so many debris flows. But all the debris flows occurred when? Well, the last 12 hours, because you had that long duration. So all hell broke loose in the last half a day of that storm sequence. All right. So what does it look like? Typically, when you have these storms and you have high intensity, long duration, you just see lots and lots of little pockmarks. Lots of little places where the pore pressure got too high, and boom, it vomits onto the slope. Here's another one, and another one, and another one. There's two real nice vomits right there coming down. And you notice here, this is all clay material, shallow bedrock right underneath, and very, very steep. And the reason we got this nice flat horse arena down here is that's where all the debris goes. And that's a great place for a horse arena because horses can run away from debris flows. Not a good place to put, young babies and small children sleeping at night, but it's a good place for a horse arena. So that's deposition typically occurs when you get to 11% slope. So here we're coming out of a confined bedrock canyon. We get out onto the regular alluvial fan here, and that's where this stuff deposits. So almost all the alluvial fans out in the western part of the United States, they're not alluvium. They are debris fans. And that material got there by debris flows. Then it gets reworked by water running over this later. So this will then have water run over it. But the way the big rocks get there is debris flows. Debris flows are what freight the large rocks. Okay, how does the destructive snout form? The Japanese have done a lot of great research on this using trigger cameras. They'd set up these video cameras 30 years ago, and then they'd have them triggered when an event comes down. And they saw at the Big Thompson flood that the destructive snout at Big Thompson was 70 feet high. So that's the problem. Is there some way you can get away from the destructive snout so you can keep this thing in a channel? You get 70 feet high, it's hard to hold in a channel. Well, what happens is, it's simple hydraulics. At the front of the debris flow, you got this very, very heavy fluid with no shear strength. At the front, you're mowing things down, like trees, shopping carts, cars, all kinds of stuff. So you're going to have greater friction right here at the front. So V2 is slower than V1. V1's going to catch up with V2, because here it's nice and smooth, slicker than snot on a doorknob. For you foreign students, snot is the stuff up in the nose, and it's slippery, low fee. Okay? And so V1 catches up with V2, and that tends to build the destructive snout. Now you also have conservation of momentum, and so all the big boulders get right up in this area and are going around like this. And these can be huge boulders. I'm going to show you some pictures of them. But they can knock down anything that gets in their way. I got one I'm going to show you that's over 35 feet across. So how do you identify these deposits? If you go someplace like the Grand Canyon, you go up any of the side canyon, the principal side canyons of the Grand Canyon, all you're going to see is debris flow deposits. 100% of the recent sediment is debris flow or landslide debris. Usually it's landslide debris gets reworked into debris flows. How do you know? Because it's matrix supported. If you look at it, it's in a matrix and it's very subangular blocks, just jumbled together without any nice stratigraphy, and you look at a fine-grained matrix support. You don't have block-to-block support, block-to-block contact. And often you see inverse sorting. And we call this intra-channel debris because it's coming down a channel and being deposited on the edges of the channel. It's banking up as it goes down the turns on either side. And so you'll see it much higher on one side of the canyon than on the other side of the canyon when you're going around a turn. And a lot of the physics of all that has all been worked out here in the last few decades. And there's actually a real good book by Oldrich Hunger and some other folks up at British Columbia on how to analyze these kinds of things and figure out what the impact loads are for retaining structures and those kinds of things. Now, the other thing about debris flows is they can flow. You can get very large class that are freighted on a very thin slurry. And you end up with something like this. This is the March 2nd, 1938 debris flow in Topanga Canyon. And you're down here on the Coast Highway, and you got, 20 inches of slurry here with, house-sized boulders sitting on top of it. Here's Topanga Canyon, 2007. One of the boulders that came down. That is a big boulder. So these things can be very problematic in terms of what kind of damage they can do depending on how much momentum they have when they strike. Now, what's going on here from a physics point of view is pretty easy to understand. It all gets to uplift force. So if we actually look at a 5-foot diameter sphere of basalt and we put it under clear water, we have an uplift force of about 4,000 pounds. And the subaqueous weight of the boulder is only 64% of its weight above water. We know that if we go swimming and we pick up somebody in the swimming pool, they don't weigh as much because their weight is buoyed by the water. If, however, the fluid is a dense fluid, a debris flow, in this case, a 65%, I think, solids, is what I used here. This is what we measured at Wrightwood. We were measuring actually numbers higher than that. Yeah, it's 65% in trained solids. We measured that in 78 at Wrightwood. And that was on the tail end of everything. That wasn't even the main event. Now that boulder only weighs 22% of its weight above water. So that's how you get all these big, huge boulders picked up and moved downstream. And when you go look at the Corps of Engineers tables for, riprap size, you can't believe it, how you got these things. Now, this happened when they first explored Hoover Dam. When they went down and they did the work on Hoover Dam, they did all these borings. And when they gutted out the canyon, they had two big surprises. 40 feet below the low water line, they found a brand new, clean 2x6 board in 40 feet deep sediments. And they go, uh-oh, how'd that get there? It's not even rotten. Well, there was a debris flow that came down Colville Wash about 25 miles upstream in 1922. Could a debris flow go down, take 40 feet of material out of the floor of the channel? Yeah. And then they got digging down deeper, and they had an inner gorge they had missed in their borings. They had hit and cored into bedrock. But the bedrock they cored into were 10, 20-foot blocks of basalt that had been brought down by debris flows in this inner gorge. They missed the inner gorge completely. In fact, that was one of the reasons they picked that site, was because it was supposed to have less excavation than the site over in Boulder Canyon. Didn't turn out to be the case. And so that became the norm on other dam sites. When they started excavating for these big dam sites out west, they'd find the debris flows move these really large blocks into the channel and crash them around. And there's no way that you could use the clear water hydraulics of the river to demonstrate those things being moved around. They weigh too much. They're up over 50 and 100, 200, 300 tons. You don't have enough water to move something like that around. So this is the real problem you have with debris flows, is the buoyancy issue. So this actually shows the debris flows at Wrightwood. Well, actually, this is La Crescenta, 1934. This is me standing in a debris flow. You're going from 64% to 22%. And if you get into something that has a lot of mica, you can actually get down to 10%. If you had 75% entrained solids, you'd be at 10%. So this is what Wrightwood looked like. This is Pelona schist. You can see this whole fan came down and just covered up all the houses. Now notice, it didn't knock the house down. It came in like a fluid. Fluid has a Poisson ratio of 0.5, so it's pushing equally in all directions. It comes down and just fills everything in. So how does it kill people? Well, the way it killed the Velez children was they were sitting there crying and screaming, and they were standing up next to the wall, and the debris came up like this. And they couldn't get out of their bedroom because the building, the next door neighbor's house had crashed into their house in the middle of the night because of the debris flow, and the next door neighbors weren't home. And the house got tweaked in simple shear like this. And when you have simple shear to the framing, you can't open the windows and you can't open the doors. That's why when you live in earthquake country, they tell you, what do you want to have? An axe. You want to have an axe to cut through a door, or you want to have a chair to break through a window and then put a blanket over the broken glass and crawl out the window. Well, these kids were in there screaming for an hour and a half before they died. They died of asphyxiation from the mud and rock building up against their chests. If they had turned around and gone like this and had a chest cavity here, they would have survived. But the firemen there, who I was very critical of, as you can imagine, the firemen wouldn't take a chance on cutting a hole in the house because they were worried they would cause the house to collapse on the children and kill them. They never dreamed that the kids would actually die from asphyxiation. But that's what happens in these things. People inside die from the weight of the soil, of the rock, pushing against them. Now, when you have a fan like this, what you need to realize is when I have a debris flow event, it's never going to come down and impact the entire fan at one time. One year it's going to go over here, another year it's going to go over here, Another year it's going to go over there. There was some stuff that I reviewed in Utah years ago where they found some geologist to support their development. And he went in here and he did some tests right here because they had a little subdivision he wanted to build here up near Ogden. And he did some age dating, carbon age dating. And he said, oh, there's no debris flow hazard here because I did some dating and there was only 3 events in the last 10,000 years. And I'm sitting there reading this thing going, oh, please. I mean, and he's assuming that whenever they have a debris flow event, it puts an equal amount of stuff across this entire fan, which is miles across. It's ridiculous. It's ludicrous. It got approved. I was the out-of-town expert, what do I know? So, what you got to watch out for in something like that. And by the way, that fan was a very famous fan in that it experienced severe problems in 1922, which were documented by a very famous geologist named Elliot Blackwelder, and then it did again in 1983. So that was 2 events just, 60 years apart, but it only happens 3 times in 10,000 years. That fan wouldn't even be there and be as prominent if it was only happened 3 times in 10,000 years. But anyway, that's, politics always has the last word. Erosive capacity. This shows Big Thompson. Big Thompson killed 144 people. Big Thompson is a good example. When the debris flow comes down, it snowballs. It picks up more and more material. The density gets higher and higher. You then have conservation of momentum. That's why it runs out so far. And so you just keep picking up loose stuff, picking up loose stuff, picking up loose stuff, picking it up, and it snowballs as you go down. Big Thompson's the biggest one we've ever had in the modern era in the United States. Debris flows also tend to envelop structures and not necessarily knock them over. They just fill everything up. This car's filled up, the house is filled up. This is Trabuco Canyon, Orange County. One near that site I told you about with a fire station last week. This one is up in Oregon, right here. And this is the one that I had in Rodeo, California. It came down, and again, it piled up behind this house, but it didn't knock the house down. Sure ruined the place, but it didn't knock the house down. Now, tailless fans. I get asked a lot of questions about tailless fans by highway departments. And this is actually California, backside Tioga Pass. And we have highways going along here across tailless fans. That's the most challenging place to try and put a highway. Do I have a debris flow risk there? Yes, I do, wherever I have a point source of moisture. So if I have a rivulet, little water ribbon fall coming down here, right there I'm going to get a debris flow. But I'm not going to get one across the entire tailless fan. I'm going to get one springing from here. It can go this way. It can go down this way. That's not uncommon at all. In fact, if you look at tailless fans, you can usually see real beautifully developed debris flow tracks in them that look like little miniature glacier U-shaped channels that are cut into them coming down. But it has to have a point source of moisture to get enough water to accrete to create that. Now, these things are all over Hawaii, but they're very hard to see because this is all heavily vegetated. And the way you can pick them out in Hawaii, if you ever go practice in Hawaii, is kukui nut trees love water. So you'll see the kukui nut trees coming down here, and then when you get down on the fan, they continue. And they disperse, just like a radiating distributary network. So that's your dead giveaway. So you're back to botany again. Botany is a good course to take. Take human sexuality and botany, okay? All right, there you go. Now, here's one. 2005, Beartooth Range, north of Yellowstone. They had a serious sudden early thaw storm. Now, that's where you get most of the debris flows that hit Wrightwood. They would always be in May. And what they are is they're early warm storms melting the snowpack. So you're getting coincident melting. So you're going from a storm that might bring in 31 inches, and you're getting another 20 inches of precipitation from coincident melting. And then you're going to get big, big problems. And here you got this whole slope got talus on it, but you're getting these concentration points off the roads and off natural ravines. And right here, you're getting some huge problems that are coming down and impacting the highway. And this highway is closed for 5 years, folks. That's how damaged it was. Let's go in and get a little closer look. There's a close-up look at the damage. This is a 2-lane, high-speed highway, and it is just gone. Now, that might look easy to fix, but it isn't. This is a scree slope. Talus fan, it's got a channel about 80 feet deep that's been gouged out by the debris flow. The road's gone, and where the road was is completely undercut here because the road paving service becomes a weir of sorts. So the road is completely gone underneath. You have to come in here with mechanically stabilized embankment, geogrids, and rebuild this whole thing. And then the real challenge is on this side. You have to remove all this material and rebuild it, put some kind of retention system in there with soil nails, and it's just a nightmare. Now, where you have a major drainage, it's a bigger nightmare because now this entire drainage has filled up with 40, 50 feet of sediment. So you've just changed the base level, and of course they got their road going across this thing with a culvert, and culvert's not going to work on something like this. The culvert's just going to get plugged up, and so you have to put in a new kind of bridge crossing with a series of box culverts here or something, bring the road up higher. This is just incredible nightmare in terms of how you're going to go out and mitigate it. Very, very big problems. And that's, look at this one in the background right there. That's a couple miles away coming down the mountain. Wow. All right. Debris flow hazard maps. The USGS has produced these, so have some of the state surveys like Colorado Geological Survey and the California Geological Survey. So has state of Washington. And what they're doing is they typically will look at the deeper seated landslides hazards. That's what this one is in red. And then they'll also look at the debris flow hazards. Now, the debris flows don't move nearly as much material, but they're rapidly moving. So these are the things that kill people. So this one destroys homes, but doesn't usually kill people because they have time to get out of it. Debris flows, on the other hand, can kill people. And here's one that triggered some federal legislation. It was the New Year's Eve 1934 storm in Montrose La Crescenta. Now, this is the same area that had a whole bunch of problems last spring because they had a big series of fires. Largest fire in Southern California history came in here and burned this area off in the late summer of 2009. So spring of 2010, they had all these canyons where they had built debris basins after this event, and those basins were filling up very, very rapidly. Well, in this 1934 storm, it killed 44 people, it destroyed 600 homes, and 600,000 cubic yards of material was deposited on the fan in one evening. It turns out, when we critically looked at that number, that's way too low. It's probably something 3 or 4 times that number that actually came down. But that's what they thought at the time. That's how much they moved at the time in order to get back in there, off the streets. So if we look at a map of it, this is actually a map they made. The shaded areas where the debris was. If I take 600,000 yards and spread it over this where they show the debris, I only get something 6 inches, 3 inches deep. That's highly unlikely, given the ground photos we have. If we take their map and put it on a modern digital elevation model, this is what it looks like. And along places like this, that's a heck of a lot more than 3 inches of material. So our new geospatial techniques we have to deal with are very, very powerful to look at these kinds of things and say, well, are these basins that they have up here really large enough? And they have to muck the basins out just constantly, and they have these huge piles of debris next to all the basins where they compact the material and then they sell it. But they haven't been able to sell much of it, of course, since the recession started in 2008. They used to sell it each year for aggregate. Now, here's one that I did years ago, about 10 years ago, down in the city of Fremont, where we made a debris flow hazard map coming out of an area right here, which was a landslide that was a mile long. It's the largest landslide in Bay Area modern history, about 20 million cubic meters of material. And we'd had some debris flows that came down this channel and got to about here. So that made everybody nervous, and so the city said to us, well, where could these things go if we had, a real event? Because this wasn't the stuff that triggered these, it was pretty small stuff. And I said, okay, well, we can do this with HEC-RAS. HEC-RAS is a hydraulic engineering center, Corps of Engineers, a river analysis system. So what I did is I took the Q100 flow for a 30-day event, and then I bulked it 300% for a bulking factor, which is what we had used up there in Marin County when we were doing that other stuff I showed you earlier with the profiles. And when we ran that, this is what happened. This thing came out through here, it bifurcated, and you could actually get a pretty good feeling. It's traveling down the roads. These are the roads. So the debris is getting stored in the roads, but every once in a while it's running into some houses, front yards, going around the houses, and coming on down here. Unfortunately, down here they had some stilling basins, and ended up filling all the stilling basins, which was good. But I thought this was really a pretty, it allowed a lot of people to go to sleep at night and not worry so much. These people weren't real happy about it, of course. And they tried to sue me, of course, and so did this guy here, because they said I was diminishing the value of their property. And fortunately, I had a good hold harmless agreement with the city, and they stepped in and protected me as their agent. Now, you can't have, in most government codes, you can't allow people to sue for issuance or denial of a permit, or everybody be suing the city all the time. So that comes under the government code statutes. So if you're working for the government doing something like this, you want to be sure and have an attorney with you who's got all that stuff figured out for you. You can get into a lot of trouble, because there's obviously people who aren't going to like the answer you give. What are some of the mitigation techniques that we can use? Well, one of the earliest ones is check dams. Everybody all over the world, this is a picture from Europe, has been using check dams going back hundreds of years. Even the Romans knew how to do check dams. And what you're doing here is you're reducing the gradient so that you bring the velocity down, and then when you pour over here, you're dispelling energy in the pour over. This breaks up the destructive snout, and that's why the Japanese are really big on check dams. They say, we're not trying to stop the debris flow, we're trying to stop the formation of the destructive snout, because we disrupt it every couple hundred feet by pouring over this high energy precipice. You have to have one heck of a good splash pad right there where it's pouring over, or these things won't work. So they're only as good as the bed scour protection at the base of each one of the check dams. But that does prevent the snout from forming and getting as high. Now, there was a lot of really interesting work done on these by the Soil Conservation Service back in the 30s and 40s when they first started up, I think around 1934, 35. And this was, again, in New Mexico, work by Luna Leopold, so the modern father of fluvial geomorphology. And the theory back then was if we put a little check dam in that was, 2 feet high, that this would parallel the fall wag of the channel. Well, that turned out not to be true. It does get a grade behind it. It's not level by any stretch, but you can see here the influence diminishes with increasing distance behind. And so if we look at the slope S, and we look at here's a 5%, 4, 3, 2, 1. This is the ratio of the height of the dam to the affected reach. So down here at a 1% grade, if we had something 2 feet high, we could go 150 times that till the next check dam. So that means 300 feet. But if we're in something that's very steep, 5% grade, we're only going to get about 65 heights. So if we had a 2-foot high drop, every 130 feet, we'd have to put in another one. So it was very useful stuff that was developed by Leopold, which the engineering profession has used. Leopold was actually trained originally as an engineer. and then got his fluvial geomorphology. Actually got his master's he got his bachelor's in civil at Wisconsin. Then worked for the Soil Conservation Service, worked out in the Pacific during World War II, got hired by Dole Pineapple, so got his master's in climatology at UCLA after the end of the war, and then after that went to Harvard and was Kirk Bryan, the great geomorphologist. He was Kirk Bryan's last PhD student there, and then he became head of the USGS Water Resources Division for 20 years. So the guy had an enormous impact because he was out instrumenting all these different channels all over the place, and had an enormous, more influence than probably any other personage in the USGS history. Debris fences and drop structures. So here's Japanese do. They use lots of drop structures, hardened drop structures. In Europe, they love to use debris fences. Debris fences are particularly effective against debris torrents and rock slides because they actually have fuse plugs on them, and they fail, and they have these cargo nets that go out and catch the debris. The downside is you have to go up and rebuild all this after a single event, which Americans don't like that at all, because that costs money. You can be stupid and just build retaining walls like this, and that's fine. The debris is going to come down, hit the retaining wall, shoot up in the air, and then come down the other side. Just don't park your car right here, because that's where it's all going to end up. So retaining walls are okay, but you still have to have someplace to store the debris. Don't be stupid. Think, where am I going to store the debris? And can I store all of it in the street? Sometimes you can, sometimes you can't. Here's the debris fences. GeoEng is the big outfit out of Switzerland. They were using these ring net barriers that were originally developed for anti-submarine nets during World War II. They kind of ran out of those in the mid-'80s or so, but they actually make them now, and then they have these fuse plugs on them, and so you can have these huge loads come into them. The fuse plug is pulled, breaks, this thing pulls out that way and catches the debris, and it's called a ring brake. And very, very effective system. The nice thing about using this is you can get GeoEng to come out there, and they really know what they're doing, and they can help you build it. California Department of Transportation has their own group that does this kind of design work. That's all they do, based out of San Luis Obispo. But they're the only state DOT there in Colorado that I know of that have a dedicated group that has very good expertise in it. Contour grading is something else. This is the Velez case, the one I was telling you about where the kids got killed. The debris flow started up here, and then came down about 1,600 feet, hit the back of the Patel residence, knocked it into the Velez residence right here, and this is where the kids were killed. And so here's a profile view of it. You can get an idea for the steepness of it. This is the one that I actually instrumented and showed you the data on, from up here on the bedrock rib and down here in the center of the colluvial-filled ravine. And how do you mitigate something like this? Well, one way you can mitigate it is to go up here and take the colluvium out, and that's what they did. So it was Alan Kropp and Associates, my former partner. He got in there and actually just took all the colluvium out of that ravine, and then they were able to rebuild the lots down here later by taking the loose material out of there. Debris basins are technology that's been used in Europe for many, many centuries, actually. LA County Flood Control District went over to Switzerland in the late 50s, looked at their basins, and then decided to build their own. They have 93 basins they maintain in Los Angeles County. And you can see when they have a major event like this coming in, the basin really gets impacted. They lose their road. All the slopes come sliding down. The San Gabriel Mountains are, all the coast ranges in Southern California, these things are rising up at about 20 millimeters a year. So highly fractured metamorphic rocks, very, very susceptible to erosion. And you're basically trying to size the basins to retain 3 times the 100-year clear water flow of the channel. So that's how they size them. They take the 100-year storm, they bulk it by a factor of 300% and say, okay, that's what we can hold in one event. Now that's what happened in La Crescenta last spring. But every time it rained, their basin filled. And they had to, because they'd had a hydrophilic soils from having the fire just a few months earlier. So they had to go out and muck it out right away. They'd have 2 or 3 days, muck it out, 100,000 yards, come out, and then next storm, fill it up again. So they were just fighting it. And they had one time where it got away from them, and I think they lost 6 homes and had a big mess. But they really dodged the bullet to only lose 6 homes. They could have lost the entire community last year. It was so bad. Where do you put these basins? Typically where you have a slope, hydraulic grade S, in the range of 8 to 15%. You do it much steeper than 15%, you're not going to get much storage behind the thing. Now, how do you design these things? I've designed a lot of them. One of the things you want to do is put bollards on the top so that you don't roll boulders over these things. The boulders can go down and plug a culvert inlet very, very easily. You want to have, so you have to have a lot of redundancy. You have to have a spillway, and you have to have a perforated riser. And I even put bollards back here so I don't get trees and stuff coming past this point. I want to try and catch a lot of the organic debris up here so I have more storage. I want to decant this silt and drain out the water through my perforated riser. And here's one out in San Bernardino, basin that filled up in one event back in the 1990s. And you can see all the debris that came out of this. This whole basin filled, and it ended up getting this entire neighborhood. This is all just mud right in here, filling all these houses right in here. Big, huge mess. So that basin, it was undersized, but the real problem here was they hadn't maintained it. They hadn't gone out here and taken the material out of here because of environmental constraints. You know, that basin had become habitat for some endangered species. And so these people became an endangered species just downstream because they were no longer protected like they thought they were. Now, LA County mucks out of their basins between 25 and 50 million cubic yards of debris each year. So that's how they're able to live in Los Angeles County. Everybody contributes to the flood control fund through an ad valorem taxation. So commercial businesses pay more for according to their acreage, and everybody else who lives in the county, including my family, you pay into it. So they have a big fund of money that's supposed to just go to the flood control. Now, back in 1985, they absolved the flood control district when they found out how much money was in this pot. You know how politicians do. They go, money? They have smell money. Oh boy. And so they took the flood control district and dissolved it and put it in the county public works department, and then took the flood control money and put it in their general fund. And all the former flood control chiefs wrote letters in the LA Times protesting it and saying, you will live to regret this decision, because in 1969 we were able to go out there and muck right in the middle of the winter because we had that money and we knew it was there. We didn't have to go through the Board of Supervisors to try and get our money. Welcome to America. It's the same thing going on at the federal level. As Abraham Lincoln says, you want to find whether people are corrupt, give them power. AWOLs. AWOLs are a solution that people came up with in Los Angeles for diverting the debris flows around the houses in Woodland Hills. That picture I showed you before. This is fine as long as you have some storage place for the material to go to down below. No problem. There's what AWOLs look like. This is one in East Los Angeles. You can see here where they put in a soil nail reinforced retaining wall here above this house, and then they made them put a AWOL above it. That doesn't look like a real likely spot for a debris flow to come down to me. This area does, up in here. So he just got guilt by association. But geologically, that's very different from that right there. But when you're dealing with regulators, you know, that's that. They don't consider stuff like that. So that's what got built there. I'm not sure it was really necessary, but because you don't see any debris flow scars or zero order basins above where that wall is. Perforated riser intakes. These are just some typical examples. This is one that's reinforced concrete, perforated riser. This is one that's made out of corrugated metal pipe that we've burned holes in. Any of these perforated intake towers are going to have to be maintained over the long term. So retention basin basically takes water and stores it so that you meter out the flow and don't overwhelm the channel downstream of the basin. And you also are taking the silt, a lot of the silt, out of the bed load, out of the channel. That's real important if you have debris flows because they have such a huge sediment load. Biggest thing is avoid flow constrictions. Here I am standing at Wrightwood. The whole problem at Wrightwood is this flow constriction right here. They have a bedrock narrows there. I told my client, which is the San Bernardino County Flood Control, if you just took this entire narrows out of here, which I could do in about 3 days for you, you wouldn't have this problem here. What happens here is the debris comes down, it drops 2,000 feet off this Blue Ridge right here, it comes down here, and it builds up to a height of about 90 feet, and then it surges through this bedrock narrows, and then it comes down and hits that culvert, which is a joke. That's a little 8x10 box culvert. What a joke for this kind of a channel. And so this dams up, and then it backs up and covers all the houses, 200 houses the last time around. So if you're messing around with something that has this much sediment, get rid of the flow constrictions like this and like that. This thing should not be there. This is completely inappropriate for that kind of a channel. But it's cheap. Now here's the channel, just the next one over. That was Heath Creek. This is the next one over. And you can see here they have a clear span bridge with a lot more capacity, and the debris just passes underneath this bridge. Here's the Palm Springs tram, which had a European designer from Austria. And the way they handled it, they put the whole tram complex right over this debris flow channel with a bridge, the bridge structure. That's smart engineering. We don't have anybody in the United States that's smart. Because back in Europe, they deal with this stuff much, much more frequently, and they have hundreds of years of experience with it. Whereas in California, you don't even have 100 years of experience with anything because it's all very, very new. So this was done by an Austrian firm, and that's the smartest thing I've ever seen built in the continental United States for being in a very tough, mountainous environment, high hazard, and they got, 40 feet clear here of freeboard. It's a very, very smart move. Armored channels. This is Colorado after the burns they had there. What you can do here is you can try to bring the debris flow down to protect the highway. You can armor the channel, try and train it, bring it down, and give the debris somewhere to get parked on a 10% grade. That's just basic channel hydraulics and basic grading. It just doesn't take you don't have to be a rocket scientist. You just got to model it with HEC-RAS. Other things I've done is putting in debris benches, very large debris benches with some kind of hardening. These are usually paving blocks. You have to have something so that when you come in here and clean it out with a skip loader, the operator doesn't dig out too much. So you have to have something that's hardened right here for them to dig against. Otherwise, they'll take out more of the hill because they get paid by the volume they take out. This is a temporary one right here, temporary basin that we built for a winterization on a grading project. That's me, about 1988, standing on. I got a little perf riser here. I got a subdrain going out, and I got a rocked overflow spillway. So if you're going to build any kind of dike, you better have a spillway. And we were lucky we never had to test that one, but it did work. Here's another one. Jersey barriers and K-rails. Highway departments love to use K-rails or Jersey barriers like this. And again, they can be easily employed. They already own them. And this can catch a certain amount of debris, not huge amounts of debris, or you can use it to train the debris to come through at a certain point where you can then attack it. And so there are design charts exist for sizing those. I've done that, and K-rails are really pretty good if you get them at least 3 inches down into the pavement. So if you come along and saw cut and take out 3 inches of pavement for passive, otherwise they just get pushed over. They slide real easy. They got to be doweled in and have 3 inches of good passive resistance to work. Here's some reinforced concrete shelters I've photographed around the world. This is the Swiss kind of design. This is in Taiwan on the Central Cross Island Highway. That's the highway that got wiped out in the earthquake in 1999. Just the whole highway on the west side of the island is gone now. And this is some of the sheds along that same highway. Both of these are actually on the east side. But you can see here where they have big, huge debris torrents, very, very rocky debris. And that's the only way you're going to provide safety for the highway. This is on the Canadian National rail line up in British Columbia, going down the Fraser River Gorge. And there, again, they have a lot of debris sheds for rock falls and debris torrents over the rail line. And you see both these have openings in the side to allow ventilation. Now for the Taiwanese, after the 99 quake, I actually designed a system for them that's much less expensive using parabolic-shaped culverts, where you cut out the downhill side and you split the road into two-lane sections and build them in culverts and then put the talus over them for your cushion, a rock cushion. And that's much less expensive than all the forming up work that you have to do for something like this. But they haven't built that yet. I think the concrete people there are not wild about it because they don't produce those culverts there. They'd have to buy them from outside the country, so that's probably not going to happen. But that would go in much quicker and be less expensive. Okay, I'm going to stop there today. Do we have any questions on anything? No questions. Okay. All right. Well, I'll see you all next Monday then.